Good morning. Welcome you all to this Radiation Oncology Physics course. Today is 4th class of this course, and today we are going to discuss about the topic interaction of radiation with matter. This is a very important topic. This topic will be referred in further classes repeatedly. So, this topic you need to understand very well, because this is actually fundamental of radiation oncology interactions and all these things. So, this is I am going to we have actually divided this topic in 2 classes. So, this is first part of this interaction of radiation with matter, and in this class our learning objective will be what is radiation, what is matter. We also discuss about ionization and the typical photon beam attenuation. We also discussing in this class about some important parameter such as half value thickness and all, and we also perform or solve some numericals in this topic. So, in this title, the interaction of radiation with matter, first we will discuss about interactions. You know that in our daily life people interact with other, and this interaction depends on the interacting people and the environment of the interactions. You can see in this slide there are various type of interaction is going on, and this interaction purpose and the process of this interaction is different, because different kind of people are interacting. Similarly, in physics also there is interactions, and it depends on the interacting entities and which environment and what is the process of this interaction. It is different from one interaction to another interactions. And then next term is of this topic is interaction of radiation with matter. Here in this slide we discuss about radiation. Now, what is radiation? Radiation is the emission or propagation of energy in any form. We know that energy can be propagated in terms of electromagnetic wave or in terms of any particulate wave and etc. So, in this radiation term we can divide this radiation in 2 categories. First is ionizing radiation and second is non-ionizing radiation. Now, what is ionizing radiation? Ionizing radiation means this radiation have sufficient energy to remove electron from its orbital shell, and this is known as ionizing radiation. And non-ionizing radiations such as visible light, ultraviolet, infrared etc., they do not have sufficient energy to remove the electron from their orbits. So, they are non-ionizing radiations. We will consider only ionizing radiation, because in radiation oncology we treat cancer patients by using ionizing radiation. There are various kinds of ionizing radiations. First type is electromagnetic radiations. They are actually X-rays and gamma rays, and the quantized form is electromagnetic radiation is photon. So, we can consider in some cases as a wave, electromagnetic wave, or in some cases as a photon particles. And another type of radiation is particulate radiation. They also having the capability of ionizing the medium when they travel the medium. And this particulate emission radiation can be divided in further two groups. One is charged particle and another is uncharged particle. Charged particle have some charge and they interact with the matter differently with the uncharged particle. The example of uncharged particles is neutrons. Again, charged particle can be divided in two groups. One is light charged particle such as electrons, beta particles, and heavy charged particles such as protons, pions, heavy ions, etc. Light charged particle, electrons, we know in earlier classes we have already discussed that light charged particle electrons have very low rest mass energy, but protons and other particulate emissions, they have higher rest mass energy. And these light charged particle and heavy charged particle, they behave or they interact with the matter differently. So when we discuss, we will categorically discuss the interactions. First, electromagnetic radiation interactions with matter. Then we discuss the charged particle. One is light charged particle and heavy charged particle and uncharged particle, that is neutron. So these are four type of actually radiations we are using in radiation oncology for treatment of cancer patients, and we are going to discuss one by one. Now in earlier classes we have also discussed about the matter. In this topic also there is a term matter, interaction of radiation with matter, and here we discuss some recap about the matter. Matter, we know that which occupies space and which have some finite mass, and this matter is composed of elements. Again for recap, we know that atom is basic, smallest and indivisible unit of any element, and atom have one central core that is very heavy. We know this is known as nucleus, and nucleus is in the nucleus we have nucleons, and there are two types. One is protons, they are positively charged, and another is neutrons, they are uncharged. And in orbit of the atom, some orbits are there around the nucleus where electrons rotate. We know they have the finite orbits, and if we consider the dimension of the atom, or what is the diameter and radius, all these things. So radius of the atom is 10 to the power 10 meter minus 10 to the power minus 10 meter, and radius of the nucleus is 10 to the power minus 15 meter. So nucleus is 10 to the power 5 times smaller than the radius of the atom. So most of the atom is a place where nothing is there, only some electrons are there, and there is a central core which has very short radius, 10 to the power 15 10 to the power minus 15 meter radius. And you can consider that if this is the nucleus, then there is a huge, it will 10 to the power 5 times higher than this nuclear radius. So most of the atomic space is vacant. Now what is ionization? It's a very important term. It will come again and again during our classes. Ionization means either a neutral atom. We know that in neutral atom, electrically neutral atom, they have same number of electrons and in the orbits, and same number of protons, positively charged protons in the nucleus. But if a electron is ejected by some external means, by receiving some energy, so then this neutral atom is positively charged and this is negatively charged, and they create a ion pair. Sometimes what happen, the electron may be captured by any neutral atom, and then this neutral atom become the negatively charged and the rest is positively charged. Now if we describe, we come to the point. First we discuss about the photon beam attenuation, photon beam interactions, and how this photon beam is described. The photon beam is described in many terminology. Actually X-ray and gamma rays emitted from either X-ray target or gamma rays is emitted from radioactive sources. So their radiation is described in the following parameter. First is fluence. Fluence is number of photon per unit area, that is dN by dA. Where here is, this is the area, a cross sectional area of a sphere of diameter of cross sectional area of dA, and these are the photon beams. Now the number of photons per unit area is known as the fluence, that is dN by dA. Now next is fluence rate. Fluence rate is fluence per unit time. Means if fluence is defined as phi, then d phi by dt is the fluence rate. Next is energy fluence. The sum of all photons energies that enter a sphere of unit cross sectional area is known as energy fluence psi, that is dE fluence. This is the sum of all photon energies per unit cross sectional area if it is a area of dA. Again there is a energy fluence rate. The energy fluence rate is energy fluence per unit time, that is d psi by dt. Now coming to the situation, that is experimental design, we have mentioned in this slide, where a number of parallel beams of incident photons is coming through these directions, and we have a collimator. Collimator means it is a type of window which purposefully gives some opening space to go through the atoms, and others photons are blocked. These photons are blocked. This is known as collimator. This is a special terminology in radiation oncology. So this is a window type thing which only allowed to pass these photons only. Now here is a attenuator which is actually absorb this much amount of photon radiation. Now in the absorber there are only 4 possibilities, which are some. First possibility is there is photon is scattered without changing any energy, just the photons having the angular change, only their scattering angle is their direction is changed, that there is no energy loss. The next term is if photon is absorbed completely. It can be happened through different kind of process or interactions, and in some cases also photon may be transmitted without interacting this absorber. As we have already mentioned that most of the volume of the atom is vacant, so there is a very fair enough chance to go this photon to transmit this photon without interacting anything. So these photons only detected by a detector. Other photons and the fourth possibility is the photon may be absorbed partially and they may be scattered in some angle. So these photons give some energy, partial energy to this attenuator, and with rest of energy the photon may be scattered in other direction. So all these scattered photons which are without any energy change, and which photons is absorbed completely, and the photon which absorbed partially and scattered in different directions, they all remove from the detector paths and they are not detectable by this detector. So this is known as photon beam attenuations. Means the number of photons will decrease from the incident number of photons. So we get a decreased number of photon after passing through a attenuator. This is a very simple design, and this experimental design where we can explain the photon beam attenuation. Now for recap, there is 4 possibilities. First is scattered photons without giving any radiation energy to the attenuator, and second is absorbed completely, third is transmitted photons, and fourth is absorbed partially and scattered photons. And only these transmitted photons without interacting with any atoms in this attenuator will be detected by this detector. Now photon beam attenuation, if we go for the formulations, from the previous experimental design, we can say that there is reduction of photon after transmitting through a attenuator. Now if the number of photon is n after attenuation, and this is number of photon is the incident photon, and reduction is dn. So if the thickness of the attenuator is dx, then we can say that dn is directly proportional to the total number of photons and to the amount thickness of the attenuator. Now if we equate these proportional equations, then we need a proportionality constant. Here it is mu, that is attenuation coefficient, and we can say that dn equal to minus mu n dx. Here minus we have given because here is a reduction of number of photons. In the above equation also may be written in terms of intensity, that is di is equal to minus mu I dx, or di, if we change this I left side, then we can left over with minus mu dx. Now integrating both sides, we get the equation as Ix is equal to I, where x is equal to 0 multiplied by e to the power minus mu x, where Ix equal to 0, that is I0 is the incident intensity and Ix is the transmitted intensity by x thickness, after x thickness. So this is actually derivation of photon beam attenuation. Now we will discuss about a very important parameter, that is half value layer, or you can say it is half value thickness, that is HVL or HVT. Now HVT is the attenuator thickness which attenuates the half of the incident intensity. Means if we reduce the intensity by half by a thickness, then the thickness is known as half value thickness. In this equation, Ix, in the equation Ix equal to I, x equal to 0, e to the power minus mu x, that is actually e to the power minus mu x. If we put x is equal to HVT, means I HVT divided by I, x equal to 0 is equal to half. So we get that HVT equal to 0.693 divided by mu. After putting log in both sides, we got this value. HVT is equal to 0.693 divided by mu. Now from this graph, this is a rectangular hyperbola. You can say that this graph will never touch this axis, because as this will the radioactivity, the photon cannot be attenuate with 0 value. it can reduce up to very negligible amount, but it will never end with a zero, land up with a zero value. So if we plot transmitted thickness intensity this side and attenuator thickness this side, then this value, that is 100% is original intensity, and this is 50%, that is half of the original intensity. This is the thickness, is known as the half value thickness. This is the thickness, we know this is actually half value thickness. And again, you have already observed from this curve, this photon beam cannot be stopped by any amount of thickness. It will never become zero. The photon intensity never becomes zero after passing through any amount of thickness. Now to solve a numerical, because it is actually application of the HBT and HBL concept, the numerical said that what will be the thickness of attenuator, which HBT is mentioned here 1.2 centimeter, for a photon beam of energy 1.25 mega electron volt, 1/10 to its original intensity. So here they have mentioned the HBT value 1.2 centimeter and the photon beam energy is 1.25 MeV, and we want to reduce the original intensity to 1/10 of its original intensity. We know that HBT equal to 0.693 divided by mu. So if we put the HBT value, we will get mu value, that is linear attenuation coefficient or proportionality coefficient of the previous equation, is we get that 0.5775 centimeter inverse, because this is unit is inverse and it is in the lower side of this fraction. So centimeter inverse. So I and I by I0 we have to do it 1/10. So that is equal to 0.1. So 0.1 equal to e to the power minus 0.5775 into x. We need to find out what is x. This is the problem. So if we logarithm the operation with both side, we get log ln 0.1 equal to, as log e to the power this 0.5775x, it will come 0.5775x, and x is equal to, we get 3.986. This is centimeter. This is centimeter. 3.986 centimeter thickness of attenuator will reduce the original intensity 1/10. So why this problem has a different impact, that if we put the value of HBT here, this 3.986 is equal to 1.2 multiplied by 3.3 centimeter, and this is actually HBT. This is actually HBT. HBT multiplied by 3.3 is able to reduce the original intensity to 1/10. So we can call this thickness as 10th value thickness. This is a different term, and this is also used for various calculations. So we got a formula from this problem that 10th value thickness is equal to 3.3 multiplied by half value thickness. Now what are the applications of HBL and TBL? We apply this half value layer or half value thickness or 10th value layer or 10th value thickness in various calculation. First of all, we use radiation protection of radiation worker and public or patients, because radiation protection is very much required for radiation worker and public, and our machine, all the equipments they are come with heavy shielding, and this shielding calculation is done using this HBL and TBL concepts. Again, the shielding calculations of installation of bunker, where our machine is located, it is huge shielding bunker. We need to prepare the design of this bunker. They are made of concrete, approximately 2.5 meter thickness of wall and 2.5 meter thickness, approximately 2.5 meter thickness of ceiling. By using this HBL and TBL, we also get a quick calculation of shielding thickness sometime to manage the emergency, where we need to provide adequate shielding to handle the emergency situation, some source exposure or some any type of exposure for public and radiation worker. And this HBL and TBL also used for protecting for calculation of shielding apparatus, shielding device of the primary radiation beam, which protects the normal tissue during the irradiation of cancer patients. Now, these are 3 steps of energy deposition. In the first step, we have already mentioned that photon beam attenuations, where the number of photons decrease or lose energy by absorption or by scattering with partial energy deposition in the medium. This is known as photon beam attenuation, and in this process the number of photon is reduced. And the next step is this energy of photon beam, which is absorbed in medium, is transferred to the secondary charge particle, which are produced because of this energy transfer. And this transfer of energy to the secondary charge particle, and these secondary charge particles are set in motion. And during this motion, the third part is energy absorption in the medium. In this part, the energetic secondary charge particles, all the energetic charge particles which are produced from interactions of, and they received some energy, and they during their movements they lose their energy by excitations or ionization process. You know that excitations, where the lower energy level electrons is moved to the higher energy level, and already we have discussed that the ionization process, because where the electron is ejected from the neutral atoms. And also the amount of energy transferred to the secondary charge particles, of the whole amount is not absorbed in the medium. A very negligible energy is lost due to the Bremsstrahlung process. We will discuss in our next class about all these type of interactions and about the Bremsstrahlung and all these things. And thank you. This is all for this class.